Okay, so yesterday we looked at arithmetic, today we're looking at geometric. So this formula we already know, geometric sequence. To find any term in a geometric sequence, we can do the first term times the common ratio. So R in this case means the common ratio. R is the common ratio. What's another name for that? If we thought of it in terms of what we just did with exponentials, that is our multiplier. That is what we're multiplying by. Okay, so I'm going to do a fun little Gauss type experiment with geometric, just like we did with arithmetic. You don't have to write this. I'll tell you what you need to write, but I want you to intensely follow along, because we're going to develop a formula for a geometric series. Okay? And it's really kind of cool, but if you're writing and trying to keep up, you're not going to. You're going to miss a lot. So just kind of watch. All right. So to find the sum of a geometric series, it's the first term plus the second term plus the third term plus the fourth term plus the da-da-da-da-da-da-da, all the way to the last term, right? Now, we could write this another way. The first term we can call g sub 1. Now, to get the second term, can't we just take that first term and multiply by a common ratio?
Mm-hmm. Yes.
Okay? And to get that third term, won't we take this one and multiply by another common ratio? So wouldn't it make it g sub 1 times r squared? And then the fourth term, wouldn't we multiply by another common ratio? So it would be g sub 1 times r to the third. And do we notice that these r's are always one less?
Yes.
So when we get down here to the end, it would be g sub 1 times r to the what? N minus 1. Okay. Now, this is going to look crazy, but it's crazy awesome. I'm going to take this whole line and repeat it up under here, except I'm going to multiply everything by r. So I'm going to multiply s times r. I'm going to multiply this first term times r. I'm going to multiply the second term times r. I'm going to multiply the third term times r. I'm going to multiply the fourth term times r. And I'm going to keep multiplying times r till I get to this very last term. Now, if I multiply this times an r, it's r to the first, right?
Yes.
And r to the n minus 1 times r to the first, when we multiply like bases, don't we add the exponents?
Yes.
So n minus 1 plus 1 is just n. Okay, so all I did was take this line and I multiplied everything through by r. Now, instead of adding, today I feel like subtracting. And there's a reason why I feel like subtracting. So when I take this minus this, it doesn't cancel. It gives me s minus sr. G sub 1 minus, well, there's no g sub 1, so I got a g sub 1. But here I have a g sub 1r, and I'm subtracting away a g sub 1r, so don't those cancel?
Yes.
And don't those cancel?
Yes.
And don't those cancel?
Yes.
And wouldn't this one be the next one right here, but I just didn't write it? Wouldn't it cancel?
Yes.
And isn't there a g sub 1 times r to the n, one before that, n minus 1 right here?
Yes.
So won't those cancel? And so the only thing I'm left with is this minus this. This minus this. Okay, does the left side, I'm not done. The math magic is not over. Does the left side have a common factor?
Yes.
S. And it leaves me 1 minus r. Does the right side have a common factor? Yeah, it's g sub 1. And that leaves me 1 minus r to the n. how do I solve for S? Divide. So the sum of a finite series is the first term times 1 minus r to the n divided by 1 minus r. That's it. Isn't that cool?
Yes.
And he figured this out as a little kid.
Did I figure it out?
No, the God did. Did you figure that out when he was little?
This is Gaussian type thinking. Same train of thought. All right, so what I've boxed is worthy of writing down.
Do you need to know that formula? Yes.
You know, you're going to be given formulas for the test, but they won't be identified as to what they are. So instead of writing a G to tell you it's geometric, I might put a T for the first term.
But last year my teacher liked to put A's on like the geometric sequences. That was evil. That's just plain evil, because like all year long we use A's for arithmetic. And so just like on the test I was like, well, that's not the right
A
equation.
lot of
but
times
that's the
on a
right
test I would
variable.
use T for a term, and that way it doesn't define it as arithmetic or geometric.
She did. It was evil. It was just plain evil.
Okay,
I
you
was
can
like,
use any variable you want.
yeah.
Okay? Alright, but right now we're in the middle of just pure geometric, so I'm using a G.
I'd like to report that.
Okay, so finite means a series that ends. So here we go. This one has the ellipses, but I say find the sum of the first 8 terms. So we're not looking at an infinite series here. We're just looking at the first 8 terms. Okay, so let's use our new little formula we developed. The sum of the first 8 terms is going to be equal to, well, let's define some things. What is the first term?
3.
3. What is the common ratio?
0.1.
0.1. And how many terms? What is in?
8.
8. So now we have everything defined that we need. So we'll plug in a 3. We'll have 1 minus 0.1 to the 8th all over 1 minus 0.1. All right, let's see if you can plug that in correctly.
There's things like on the homework last night, when we had stuff like this, I didn't use the formula, I just did it. It just seemed easier.
Okay.
Will you count off if we do that on the test?
If you can write something down and get it right, I'm cool with that.
So I don't have to use the formula, as long as I get it.
Now, what if my question says, find the sum of the first 300 terms?
Well, yeah, I would use it for that, but
Okay.
that's not necessary.
Nope, this one's not. Okay, Doug, what's the answer without the formula?
Hold on. 0.00000003.
No.
3.
Oh, Doug, go for it. No, I have
7.3. Okay? Now, you might be tempted when you look at your calculator to say this is 0.3 repeating,
It's not.
but it's not, because we ended 8 terms.
Yeah.
If we did it, yeah, if we did it infinitely, we might get the repeating part. But right here, we just have the 7. Okay, you try number 2. about to find out if you know how to put a negative into your calculator. Okay, so the answer is negative 236,192. Okay, because when we raise that negative to an even power, it becomes positive, but when we do 1 minus that, it becomes negative.
So it can be like 1 plus 3 to 10?
No, because it's always 1 minus r to the n, and so PEMDAS tells us we have to do this power first before we can do that subtraction. Okay. Okay, so here we have a geometric series, and it's definitely finite because it ends at 625. So we can clearly see the first term is 1/25. We can find the common ratio. Now, if you can't look at this and tell what it is, if you take a term and divide by the previous term, it always gives you the common ratio. You see that the common ratio is positive 5. Now, n is what we don't know. But they did give us the last term. G sub n is 625. So how can we find n? We can go back to the formula from last year. We know that our final term is 625. Our first term is 1/25. Our common ratio is 5. So to solve, we would multiply by 25. And we would get 15,625, yes.
Yeah, I think it's
Yes, you do. We're solving for an exponent. So we take, unless you know what power to raise 5 to get 15,625.
obviously.
About
Okay? So it is 6 equals n minus 1. So 7 is n.
It's 5 to the 7.
Can you
No, it's
do,
5
do
to
you
the
have
6.
to do ln or can you do log?
It's not 5 to the 7.
It'd be 5 to the 6.
5 to the 8 minus 1.
Just wait.
Right.
Do
Uh-huh.
you
It's
have
5
to
to
do
the
an
6.
natural log? Can you just do regular log?
You can do either one.
Excellent.
All right, so now I've got n, and I've got the first term, and I've got the common ratio. So I can say the sum of the first 7 terms is the first term times 1 minus the ratio raised to the 7th over 1 minus the ratio. And so the sum of the first 7 terms is exactly okay.
Did you say you had a quesadilla?
Do we get it?
Yes.
All right, because some of my students need to get up and move around. We're about to.
Are we going outside?
No.
You got him so excited.
All right. Here are our graphs of some geometric sequences. Now, what I want you to imagine is that even though they end here, imagine that they continue on forever. Imagine that they continue forever. Which one do you think we can find the sum of if it goes on forever? Which one can we find the sum of? If you think it's A, you go stand over there. If you think it's B, you come stand over here. If you think it's C, you go back there, and D, you go over there. Go! Everyone must get up and move.
I just follow Sarah Grace.
This little bee.
All of the above.
Go with the movie.
Sarah's in the middle.
You can't go wrong with
No, you gotta make a decision.
I'm doing
Wait,
wait.
I'm just surrogate.
I'm just thinking
You
about
gotta make a decision.
Wait.
But I'm saying be I'm gonna just stay by the village.
All right.
Let's check
Count,
this.
please count how many people are standing at A and report.
I just followed Sarah Grace.
I follow this movie.
Because I didn't hear
Eric. Eric, where are you?
Eric, you gotta make a decision, bud.
I'm over here, I guess. Look, I was just gonna wait till which one of these was right. and then-
10. So we have 10 that chose A. Okay, so how many do we have at B, guys?
9.
We have 9 that have chosen B.
We got a little Brady over there.
Brady, can you report to me how many are at C?
Look at Brady with all his friends.
1.
One is at C. And Ben, can you report? Ben says 1
Hey, there's
is at D. Is everybody standing somewhere? Okay, cool.
That kid's not even.
All right. So as this one continues forever, won't it just continue to approach the asymptote?
Yes.
And so those numbers get smaller and smaller and smaller
I
and
think
smaller.
that's right.
And this one, as it continues forever, won't these get bigger and bigger and bigger and bigger and bigger and bigger and bigger forever?
You could just put infinity.
And as this one, it looks like it's bouncing back and forth, getting closer,
There were 2 back here.
to,
And 9.
yeah, look at this one. And this one, it's getting further and further and further and further away.
So which one's right?
C.
Is it
Does
just
anybody else want to move?
No.
It's none.
It's all of these.
Isn't it just infinity? I mean,
It's all of them.
You can't group me, and none of them ever end.
Yeah.
I'm gonna sit down.
They're all just
I'll boil it now.
Watch it be all over.
It's
I
always
wish you started here.
ends
Come on
will
with
be
this.
on the thing.
What? I'm going next year.
All right.
Oh, wait.
Okay, so now I think Eric is still at A. So I'll say now we're 5 at A. B is also down to 5. Brady is making friends rapidly. He is up to how many?
8.
I was the first.
8. You were Brady's first friend. All right, Ben
I know you're right.
All right, and Ben found a friend also. He's up to
Good job, Ben. You can
2.
make all kinds of it.
Invalid. His mom's baby, right?
Okay. All right. Now, some people left A,
What if that's the right answer all along?
I'll feel so sad.
and as it gets closer and closer and closer to 0, isn't it almost like adding 0?
Yeah.
And can't we eventually sum that up if we're just adding 0?
That's what I was thinking.
So A is a winner. Okay, but this one, these terms get bigger and bigger and bigger and bigger and bigger and bigger forever. Can we bound that?
It's all.
No.
Yes, we can.
No, we can't.
You just keep adding.
But we can't come to one sum. The sum continuously grows forever.
Until the
that
time-
one.
But take a look at this one. Eventually, isn't this one like adding
Yeah.
0?
I don't understand why you could add 0.
Yes.
It's a
I was right 2
number.
times.
You will eventually.
I
know how to choose my right people.
And then
But what about this one?
Correct.
It's all
No.
Because without
No.
that one, they would.
It never
I don't understand why you
stops.
add
You
0
add it.
when they are numbers.
No.
All right, we're going to look at it algebraically next instead of graphically. So,
I mean, yeah, that makes you numbers.
all right, you may have a seat. You may have a seat.
Why are we allowed to add 0 instead of 0?
Well, because if I type this into your calculator,
I was like, think of a really small number. 6
0.5, because wouldn't 0.5 give me a decay type function? Let's do 0.5 to the 20th power.
Why? No, I don't want to do that.
Oh, that's.
Is it small? Did it put it in scientific notation?
It did.
Okay, let's do 20 wasn't a big exponent though.
6.22 times 10 to the 23rd facility.
I like that number.
got you a number.
Let's do
100.
0.5 to the 100.
I
Oh.
get on to.
Is it smaller?
Yes.
If I graphed it, would it look like it's sitting on the x-axis?
Yes.
But is it really, 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 really close?
Yes.
Okay.
Yes.
Now, then, I would like you to do 0.5 to the 1,000 power.
Zero.
Edward says don't do it.
Zero.
Just give up. What did your calculator round it to?
Zero. It was that
It
Because
does it
it is
900
so infinitesimally small, that's not the word, that it's pretty much zero. Alright, so, if you were given an exponential function, such as y equals 3 r raised to the n minus 1. So if r is greater than 1, can we sum up everything? No, we can't bound it. It's nothing. We cannot bound it. It's another word besides bound, because I said it twice instead of coming up with a different word.
every time I
Can't
read
contain it.
Yeah, contain, thank you.
Yes.
No. Alright, if we tried to find the sum of this, the graph looks like this if r is 1. What is the sum of 3 if you add it up forever? You can't find it, can you? No. Can't find it. Alright, with this one, do you see that as n grows larger and larger and larger and larger and larger, the value of this function is almost 0. So this one is a yes. Can we, if r is exactly equal to 0, can we find it? Yeah,
Yeah.
because 0 plus 0 forever is still 0. Thank you. Okay, and this one is a yes, and this one is a no. Because if the graph is approaching 0, then eventually you could argue that it approximately has a value of 0. And our calculator even told us that 0.5 to the 1,000 power is 0. Now, is it 0 exactly? No.
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 It doesn't care.
It really bugs me that it's not 0.
Okay, so let's do the infinite sum. Okay, don't write this first thing. Do not write this. We're thinking. Okay, so this was our equation, our formula a moment ago. We decided that r, to find an infinite sum, that r has to be between -1 and +1. Didn't we? We said no. We said no. We said yes. We said yes. We said yes. We said no.
No.
The only one that works are between -1 and +1. So if I took a fraction and raised it to an infinitely large number, our calculators just told us that approximates to be 0, doesn't it? And what is 1 minus 0? 1. And what is 1 times g sub 1?
G sub y.
Alright, so here's our formula. This is it.
That's really easy now.
That's so much easier.
It is easier.
Why?
Don't question it, just accept it.
Anytime I explain why at the end, you're all like, huh?
But you explained why on the last one.
No, we don't need
No,
to.
she
I just
explained
explained why. I said if this is raised to an infinitely large number, it approaches zero. It's approximately zero.
Is this gonna be our test?
The use of the formulas, yes. Okay, so can we find this infinite sum? See the ellipsis? Goes on forever. Can we find that sum?
If we want
I mean, if you want
to. If we want to.
No. And the reason we can't is because R is 2. Does R fall in our acceptable range?
No.
No. Can we find this one?
Yes.
Yes. Because R is what? 1/2. Can we find this one? Here. Here we can?
Yes.
Yes.
Negative 1/3.
R is negative 1/3. Okay, so here comes your homework.
Holy, this will be.
I don't want homework.